Okay, so a short reminder. In that last time we learned about the Fourier transform, so we found that there is a transformation like this on the real line, which is the integral from minus infinity to plus infinity of dx u of minus ipx f of x, and there is an inverse transformation given by this formula. And there are also various variations of this relation. There is transformation between circle and integer numbers when we compute Fourier series for periodic functions, or there is a finite dimensional version of it. And when we checked this relation or its counterpart for circle and integers, we came to the concept of generalized functions. Which are functionals, which are linear functionals on the space of on the space of C infinity functions with compact support on R, or in principle it can be on S1 or on Rn. In principle, they can be defined on any manifold. Yeah. So, and the the main thing which we used here was the idea of weak convergence of a sequence of usual functions to generalized function. So we can say that a sequence of functions f n converge to f, where f is a generalized function. If for any phi in the space of C infinity functions with compact support, in the sequence of pairings between this generalized function and phi converges to pairing between this limiting generalized function. And the main example, which is similar to everything else, is the convergence of a delta-like sequence to the delta function. One example of delta X sequences was this delta epsilon of x is epsilon over pi epsilon squared plus x squared. And the sequence converges to a delta function. So pictorially it looks like this. We have a sequence of these bell-shaped functions which become more and more narrow. And finally they come to finally they converge to a generalized function, which is not a function anymore. So it is something concentrated literally at zero. So and this can be defined, so this limiting function can be defined only in this sense as a function on the space of as infinity functions by saying that for any phi, this pairing between delta and phi should equal to phi of 0. So it's a definition of this limiting function, a limiting generalized function. And we could prove that this delta X sequence actually converges to this generalized function. And of course, it's not the only example. We can write infinitely many different delta X sequences that converge in this way. So, and the idea was that we could compute something for such a delta X sequence at finite epsilon, and then take the limit at the very end. So we could use it to prove this formula about direct and inverse Fourier transform. So the formula which we needed is well, there are several formulas that we needed. One is this. So this integral is not very well defined as is because it is divergent. But if add here minus epsilon absolute value of pi, then this becomes delta x becomes an element of delta x sequence, and this is something we can work with. But also this can be viewed formally. In a sense, what is written here? You can understand it in the following way: that there is the integral d power phi IPX times 1, and this equals to delta of x. So we are computing the inverse Fourier transform of a function that equals to 1. But let us formally compute this Fourier transform in the opposite direction. So this is f of x, and this is f tilde of p. Now, what happens if you compute this integral? Yes. Yes. And so as expected. Mm. And this left-hand side can be written as a pairing between e to minus IPX paired, well, in what order? Maybe. So if you write generalized function in the first place, you can write it like this. Mm. So here, of course, this function is not in this space, but it is a usual situation that this notion can be extended. So if you work with some particular function, then this notion can be extended to a more general space of test functions. So, there is this idea that generalized functions exist and can be used in computations like this. Mm, uh, mm, and I'm telling you this idea to justify some of the things we computed earlier. So one place was, of course, this composition of the inverse Fourier transform, in which we had to compute integrals or sums like this. So another example is the sum. Sum over integers into n x is the sum of delta of x minus 2 pi n. And again, it appeared as this regularized sum. Yes, so it was one thing that had to be justified. Another thing is related to the pictures we were drawing at the very beginning. Of. By the way, I think I don't have all your emails, all right? So. Is it true? Was so yeah. Yeah. Yes. So what we studied were such solutions of the wave equation that had uh, had a triangular shape. So we studied the solutions of the wave equation, which looked like this. This was u of t of 0x, and ut of 0x was 0. And we studied a solution of the wave equation with this initial condition. So its evolution looked like this. I'm not drawing the intermediate step, but if you wait for some time, and then this solution looks like two triangles shifted by t and minus t. The problem, and this was obtained formally by simply saying that in this case u of t and x equals to 1/2 u0 of t plus x plus t plus u0 of x minus t. And we don't care about the differentiability. So so the problem here is that these second derivatives written in the equation do not exist in the following sense that let us draw the first derivative of this function. Ux of 0 and x. So it equals to 0 on this interval. It equals to 2 on this interval. And 2 equals to something, well, to be honest, it's not defined at point -1. It's discontinuous here. And we have the same situation at 0. So here it is -2. So there are two possible ways to resolve this problem. One way is to say that we can actually differentiate even this function, and what is your guess about what is your guess for second derivative of such a function? Yes, because so So you see that this function is zero for all intervals except points -1, 1, and 0. So and we see that the integral of the second derivative contains a jump at point -1, which means that if we integrate it from minus epsilon -1 minus epsilon to -1 plus epsilon, then it should equal to 1. So it means that we have a delta function here with a positive sign. Then when we integrate between this and this point, we see that it has a negative jump equal to -2. So there is another delta function here. And there is one more delta function at point 1. So overall, we can write that this second derivative equals to delta of x minus 1 plus delta of x plus 1 minus 2 delta of x. And if you want to check that this equation is indeed satisfied by this function, then we simply substitute the solution that depends on x plus t and x minus t. And if you differentiate it twice in x or twice in t, then it will be all the same, because these functions depend on x plus t and x minus t. So these two terms will actually cancel. But the only thing is that they belong to generalized functions. So this was one way to solve this problem. We can call it resolution 1. You can simply allow differentiating discontinuous functions and working on the space of generalized functions. So, but it doesn't look like something absolutely rigorous, because, for example, why should we call u or its derivative a generalized function? Like, are we studying them as functions functionals on some space? So if you try to make it truly rigorous, then we should introduce a new object which is called the weak form of equation. So it can be obtained using the idea of this infinity test functions. So we can say that Let's simply take our equation, probably with an integral right hand side, equals to some function f. And let's go from this equation to its pairing with an arbitrary test function. Let us write so in the left-hand side, this pairing is given by the integral, and also in the right-hand side. So we can write that this is integral from minus to plus infinity of u tt minus u xx minus f times phi integral over dx dt. Well, it's double integral in this limit, and this equals to 0. No, both go from minus to plus infinity. If you care about initial, yes, it depends on what initial conditions we want to study, but I don't want to think about the boundary terms, so I say that initial conditions are 0 at minus infinity or at some fixed time, or even at 0. So but of course, this can be upgraded for non-trivial initial conditions. Actually, we can start from this case, and then remove where is eraser? So we can actually start from this, and then see how it works. So the idea is that if you want to study functions like this with undefined derivatives, it makes sense to integrate everything by parts. So let's first take care about the x part. So first, the pairing between uxx and phi is the integral from minus to plus infinity dx so first integral by parts gives ux phi from minus to plus infinity, which is 0 because phi has a compact support, minus phi x ux dx. So this equals to minus pairing between ux and phi x. And then we can do the same integration by parts once again. So this goes to 0. We can do the same integration by parts. And second term is a similar pairing between second time derivative of u and phi. And this equals to so here we get the boundary term. We get two boundary terms, one of which is 0. We have ut times phi from 0 to plus infinity. Minus go from 0 to plus infinity ut phi t dt. So this integral has a non-zero value at 0, at the lower limit. So it equals to minus u1 of x phi of x. So sorry, yes, it's true. 0x. Yeah, let's find 0. Yes, so we have two terms. A pairing between minus u1 of x phi of 0x minus a pairing between u t phi t. And then we integrate it by parts once again, and we will get another term with a pairing between u0 and x derivative of phi at 0. So after all, it will be minus pairing of u1 of x phi of 0 and x plus u0 of x phi t of 0 and x plus u phi dt. So the u1 and u0 are initial conditions for our equation at 0. So it is ut of 0 and x. Oh, so, yes, and this is u of 0 and x. And so do you have any questions about this? So if I now combine everything, we get the weak form of the wave equation. Maybe I can write it here. So we have a pairing between u and phi t minus phi xx minus f minus this term plus this term so this should hold for arbitrary test function phi. So this this is called a weak form of the wave equation. This is called a weak form. But wait, let me think. Yes, because I made some stupid mistake. Yes, thank you. There is another term minus pairing between f and phi. Yeah, so they all should be paired with the test function. All right, thank you. Yes. Where is this term? So and this this equation is called weak or weak form because conditions on initial constraints on initial conditions and on the solution of this equation itself are much weaker than originally. In a sense, now they should just be continuous, or maybe well, maybe let's ask them to be continuous. We don't need them to be differentiable anymore. So and of course, if the weak form of the wave equation is satisfied, and u is twice differentiable, then we can prove that the original wave equation is satisfied as well, because we can simply integrate all these terms by parts back, and if it is satisfied for arbitrary test function, then we can simply take this test function mm, equal to 1 at some small at some arbitrarily small interval, and prove that the equation itself should vanish on this interval. So mm, uh, so we can say that if a weak form is satisfied, u is C2 of R2, then original wave equation is also satisfied. Oh, but it's some way to make rigorous our original computation with delta functions, and to make this solution rigorous as well. So. So if you want, for example, to check that this solution satisfies the weak equation, we can try to substitute into the definition, so and see what happens. That u of t and x given by arbitrary function of t minus x satisfies the weak form of the wave equation, even if this function is not differentiable. So we want to check that for any test function phi with pairing between f of t minus x with phi t minus phi So question is why is it true? So we have the integral from minus to plus infinity of f of t minus x let us first write it as the integral in in t. So let me with t minus x or x minus t. Let's write it x minus t. Simplicity. So let's perform the change of coordinates in this integral. Oh, sorry. I should have written f of x. So in this integral, phi dt of t and x plus t means that we differentiate in the first argument, and maybe let me write it like this: phi 1 in the sense that it is a derivative in the first argument of this function, and another term is phi 2 2 of t and x plus t. So we have an expression like this. Mm. And what I want to say that in order for this integral to vanish, we should find that this expression is a time derivative of something. Yes. So let us try to find this expression. So in principle, we have two candidates to differentiate, and let's look at both of them. So we have a derivative of this function in the first argument, t and x plus t. And if we differentiate it in dt, then we get what? We get phi 1 when we differentiate it in first argument. Plus another derivative when we differentiate it in second argument, phi 1 2 of t and x plus t. And we have a derivative in the second argument. So again, phi 1 2 of tx plus t plus phi 2 2. And we see that if you subtract those two, then we find precisely this expression. So we can write that it is integral from minus infinity to plus infinity dt dx fx d dt of phi 1 of t and x plus t minus phi 2 of t and x plus t. So, and since it is a C-infinity function with compact support, and it is integrated over the whole space, then it equals to this time integral equals to 0. So is it fine? Yes. It's time derivative of something. So we get it at uh, different infinities. This vanishes. Mm. But you see that it is uh, actually a bit too rigorous. So of course we can prove that this equation satisfied in the weak form, but it's easier to say that if some function is not differentiable enough, but it has this form f of x1 minus t, then it satisfies this weak form of equation. Mm. So, uh, mm, yes, even if it is not differentiable enough. Yes. So um, I would say, mm, mm, no, let me think. No, I would say no, because most of the functions that appear somewhere in physical problems are smooth enough, but it is always useful to extend the class of functions we can work with to be able to do something in the intermediate steps. So. Mm. Um, uh, well, there are uh, 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 two possible options for the wave equation. We can either say that it is defined on a half line and it has zero initial conditions. But we can also say that it is defined on the whole R2 and its initial conditions are like solution should be zero if you go sufficiently mm, long back in time. So, in a sense, we can place on this line of initial conditions infinitely far in the past. Mm. Hmm? Mhm. Yes. Yes. We simply differentiate it twice and see that two derivatives cancel. Like in this case, like f uh, d in dt of f of t minus x is f prime of t minus x d in dx f of t minus x equals minus f prime of t minus x d2 in dt squared f of t minus x is f 2 prime of t minus x d in dx of uh, so there are just two second derivatives that cancel. Mm-hmm. Yes. Oh, but we can do the same for the second part of solution. It will be literally the same, just the shift will be in the opposite direction. Ah, no, no, of course no. It's not because we can. Was actually solving it for x minus t, but it doesn't matter. Or the same arguments work in that case as well. We'll simply have x minus t, and this second sign will be different. So that's all. So I don't want to check it on the blackboard, so let us leave it as an exercise. But so should work because it's just a way to define the wave equation satisfied by less regular functions. Is it okay or not? And since you can do exact same computation for f of x plus t, so you would need to shift this in the opposite direction and check that it is still satisfied. So let me raise this. So one extra advantage of this weak form of equation is that we can solve it with a more general right-hand side. Because you see that the only requirement for the right hand side is that well, in this form is that well, maybe let's look here. So the only requirement for f in the right hand side is that it should be pairable with infinity functions with compact support. So in particular, we can take this f to be a delta function. Let me check. With a delta function on the right hand side. Maybe better to say first that we can at least define this equation. So we can solve the wave equation. Well, sorry, let me say it. So, oh, sorry. The equation we want to solve is this. Delta of t times delta of x. Well, the weak form of this equation is the following: is u is phi t minus phi x equals to delta of t delta of x with phi, which equals to phi of 0 and 0. So this equation makes sense, but so if you want to actually solve it, or to check that some function is a solution of this equation, it is better to switch to coordinates t plus x and maybe x plus t and x minus t. Yes. So equation this, and we are interested in its solution. So who can tell who dx and dx and deta are? So dxi acting on xi should give 1, and acting on eta should give 0. So it is 1/2 dx plus dt, and deta is 1/2 of dx minus dt. Right? So if you act with this derivative here, it gives 0, and this acts by 0 on psi. So we can write that this mm, pairing between u and 4 phi psi eta equals to 5 0 and 0. And when we write this pairing, then it is a kind of t and x pairing. In a sense, this equals to integral from minus to plus infinity in dx and dt. But since x and t are given by this Jacobian transformation to psi and eta is 2. So or 1/2 depending on direction. So this can be written as 1/2 integral dxi deta, which is psi eta pairing. So if we write everything in new coordinates, then we have an equation that pairing between u and 2 and between u and phi psi eta computed for coordinates psi and eta equals to 1/2 phi of 0, 0. Hmm?
When we change coordinates, the derivative changes sign. So it's a u comma -4.
Yes, I think. Yeah, thanks. Yes, it's true. Thanks. Let me think. Uh, what kind of coordinates do we actually want? Maybe let us choose mm, mm, yeah, maybe indeed, and this is the right choice of coordinates here. Thanks. So it will be this. So we now want to solve this equation, and to guess the solution of it, let us try to rewrite it back to the usual form. So we can write that this equation is more or less equivalent to the following one, that u of psi eta paired with phi equals to 1/2 of phi 0, 0. So u psi eta equals to 1/2 of delta function of psi delta function of eta. And so we can conclude that at least one of the solution of this equation is that u equals to a product of two theta functions. Beside theta functions, in a sense. But so this was not a rigorous computation, of course. But to do everything rigorously, let us switch to a simpler case. So the simple equation is the following. We want to solve an equation that u prime of x equals to a delta function. So the weak form of this equation will be the pairing between u and phi prime, equals to phi of 0. And to find such u, we can choose different test functions. So let me first we want to prove that solution of this equation is constant everywhere except 0. And in order to check this, we choose test functions that behave like this. They are infinitely differentiable everywhere, but they are non-zero only in some small domains from y minus epsilon to y plus epsilon. So for such a choice of a test function, we see that integral from 1 minus y minus epsilon to y plus epsilon of maybe let me like this. Oh, is equals to 0, and here we can integrate this by parts and say that integral from y minus epsilon to y plus epsilon for u prime phi dx equals to 0. So u prime is equal to 0 in this domain. So and the next step is to see what precisely happens at 0. Maybe erase this. So in this case, we can choose this uh, test function around concentrated around 0. And says the following, that the integral from minus epsilon to plus epsilon who knows wait, so let me think for a while. Let, let me say this way. We know that phi is that u is constant everywhere except 0. For we already know this from a solution of our equation away from 0. And now we want to see what happens precisely at 0. So let us write this this pairing, taking this into account. So integral from minus infinity to plus infinity u phi of x, phi prime of x dx can be split into two parts, from 0 to infinity and from minus infinity to 0. So, and now since u is a constant, it can be integrated by parts. So it's not only constant, it equals to u plus and u minus. So we can substitute that it equals to u plus and this equals to u minus. So we can write that it is u plus, in this case minus u plus, times phi of 0 of 0 plus, and this is 0 minus, plus u minus phi of 0 minus. Maybe you can write 0 plus plus epsilon, 0 minus epsilon. And and since phi's are from this space of significant functions with compact support, they both go to phi of 0. Yes, so this is the left-hand side of our equation. This is pairing between phi and u and phi prime. And the right-hand side of this equation should be minus phi of 0. So we get an equation that u minus that u plus minus u minus times phi of 0 equals to phi of 0. So u plus minus u minus equals to 1. And so the general solution of this weak equation is what? U of x equals some constant plus heaviside theta of x. So this is a function that equals to 1 for positive x and 0 for negative. And it's not defined at 0. So we can define it by 1/2 there, but in general it's not defined. So see, there was some problem with discontinuity that we had to consider two different limits of this function. But in principle, this could also be resolved if we integrated that equation one more time. In a sense, we could write here the integral of u, and so here we would have phi 2 primes. So this is a more or less rigorous solution of this weak equation, and if you want to derive it simpler, if you want some technical trick, then it works like this. So we have an equation that prime of x equals to delta of x. And we first noted that if x is not 0, then u is constant. And second, if you want to study what happens at 0, we simply take this equation and integrate from 0 minus epsilon to 0 plus epsilon. Integrate from minus epsilon to plus epsilon of u prime of x equals to 1, because it is the integral of delta function on one side. On the other side, it is dx. On the other side, it is u of plus epsilon minus u of minus epsilon. Yeah, and now about the meaning of this theta function. Mm. So we solved this equation with the delta function on the right hand side to be able to find the green function of this equation. Mm. So if you solve it with arbitrary right hand side, so in this case it is easy to understand what should be written there. So if you want to solve the equation that u prime of x equals to some function f of x, then of course it has many solutions defined up to a constant. But if this function is integrable from minus infinity, we can simply say that u of x in the integral from minus infinity to x f of x prime dx prime. Or, which is the same, we can say that it is integral from minus infinity to plus infinity theta heavy side of x minus x prime f of x prime dx prime. So it is the same function that we obtained solving our equation with delta function on the right hand side. And if you go back to the wave equation, then maybe this. I don't want to do everything rigorously, but we can simply say that it is the same equation written independently for each coordinate. So uh, we can say that a solution of this equation with delta function on the right hand side is given by two heaviside thetas. I missed 1/2 here. So if I wrote this correctly, then this function is non-zero in this domain. Maybe this should actually be with the negative side. Maybe this. Yeah, this should have. They should both have negative signs. Minus t minus x and minus t plus x. So solution of this equation gives rise to this combination of theta functions. And if we go back to solution of the inhomogeneous equation, then we remember the same formula, that u of t and x is integral over dt prime dx prime half of this heavy side minus t minus t prime minus x prime times f of t prime x prime. Solution of this equation. One half. So do you have any questions? Okay, then thanks for your attention. See you tomorrow.